طيب. Now we have the force acting on a spring, not a string. A spring which is you know the spring. Without any force, the spring has its length and its mass, and its mass supposed to be 0. Assume this length is x naught. If I push it, then it will be shorter. Right? If I pull it, it will be longer. In this case, we have a new length. Also in this case, we have a new length. We can name this length x final, for example. And this is x initial, or x0, x1, x1, x2. The important thing in our study is the difference between these two lengths. And we will use this difference. And I will give you the difference. And you need to deal with this difference. Or it is this distance, which is delta x, between the wrist and the final position, because we have a force. We can name it delta x or simply x. Okay? If I have a spring, I need to push it. And I can use the spring horizontally or vertically. If our spring any question about anything in the lecture, please? I'll go to the example just to understand what we need to discuss. If I put a mass and my x node is equal, for example, to 0.5 meters, half a meter. If I put a mass, this mass has a weight downward. The effect of this mass is pushing the spring, not pulling it. I will have a decrease in its length because it has a weight downward. Maybe the length of the spring, x final, will be equal to 0.2 meters. If this mass is equal to 10 kilograms, its weight is almost 100 newtons. If I approximate G to 10, right? Right? All of us like to use G as 10, not 9.8. Okay, now, what if I use another mass, which is a 20? Here. The next 20. What if I use a mass 5 kilograms? Or 20? 5. Let us use a 5. What do you expect about the compression of the spring? Is it less or more? Less, because I have little less force. What if I put 20 kilograms? Then the spring will be pushed more and will be compressed more. Okay. So we have a force acting on a spring. We need a law, a formula to deal with this. We have Newton's law, F is equal to ma. But we have a spring. we have mass, but sometimes we can do this experiment, just like in the nose. I can push by F. There is no mass, there is no acceleration because the spring, just after pushing it, it's stationary. We have another experiment or experimental person, his name was Hooke. And we have the spring force law or Hooke's law, which is F of is equal to negative K X. X is the change in length. K, it is a constant. Represent the properties of that spring. Minus the minus sign. If I push the spring to the left, then the spring will push me to the right. Opposite. This is a restoring force. Restoring means if I go to the right, this restoring will push me to the left. Then I have the minus sign. Because of that. The magnitude of this force without the minus sign. K is a constant, just like mu, what we called from before. This is for the spring. You know that you have your pen. It's a spring inside it. It is easy to move it. Some springs are easy to play with, but some springs are hard to push them or to expand them. If K, for example, if K equal to 1 and its unit, how can I find its unit? K is equal to F over X over X over X. F is in newtons, X is meters. Then the units of K is newtons for over meter, right? If K is 1 Newton per meter, and I have another K, K2 is 100 Newton per meter. I have this spring and this spring. The first spring, if I push it by 1 Newton, I can expand it by a meter. The second spring, I need 100 Newton to expand it by a meter. It is more difficult. Using this law, you can see and find different Ks for different springs. Look at the example that below the bottom of that page. If we have for the first one, M is equal to 60 kilogram on the top of a spring, and X equal to 30 centimeters, which is equal to 0.3 meters. Find K. K is equal to F over X. F is the weight. X is 0.3. The weight is mg. M is 60 over 0.3. This will be equal to 1,961 point something Newton per meter. It's just a simple example, just like Newton's law. And you can find that for any mass. You have 4 examples. Any mass, any distance, any spring, constant. Any questions about springs, forces,